What problem does the proposed long context frontiers LOFT benchmark aim to solve in the field of deep learning?
The proposed long context frontiers LOFT benchmark aims to solve the problem of inadequate evaluation of long context language models, LCLMs, in the field of deep learning. The existing benchmarks fall short in evaluating LCLMs on truly long context tasks useful in real-world applications, relying on synthetic tasks or fixed-length datasets that do not keep pace with the evolving definition of long context. LOFT addresses this by introducing a suite of tasks spanning text, visual, and audio modalities, with increasing context lengths up to 1 million tokens that can be further extended. It focuses on areas where LCLMs have the potential for disruption, such as retrieval, retrieval-augmented generation, SQL-like reasoning, and many-shot in-context learning. LOFT allows for rigorous evaluation of LCLMs on complex tasks, stressing their performance on paradigm-shifting tasks and pushing them to their limits to gauge their real-world impact.
How does the long context frontiers LOFT benchmark work, and can you illustrate its methodology step by step?
The long context frontiers LOFT benchmark works by providing a suite of tasks across text, visual, and audio modalities to push long context language models, LCLMs, to their limits and assess their real-world impact. The benchmark consists of 6 tasks with 35 datasets, allowing for automatic creation of increasing context lengths, currently extending up to 1 million tokens. LOFT focuses on areas where LCLMs can disrupt traditional methods, such as retrieval, retrieval-augmented generation, RAG, SQL-like reasoning, and many-shot in-context learning, ICL. The benchmark enables evaluation of LCLMs on tasks like retrieving information from a corpus, processing databases as text, and scaling the number of examples for learning. The methodology of LOFT involves constructing shared corpora for tasks like retrieval and RAG, where all queries share a single corpus containing gold passages from few-shot, development, and test queries. The corpora are carefully formatted to mitigate causal attention effects and ensure fair comparison among models. For tasks like SQL, databases are selected based on context length limits, with larger databases reserved for longer context lengths. The benchmark also introduces corpus in context, CIC prompting, where large corpora are directly ingested by LCLMs within their context window, enabling a novel approach for solving tasks. In summary, LOFT works by providing a diverse set of tasks and datasets across modalities, allowing for automatic creation of increasing context lengths, shared corpora construction, and innovative CIC prompting methodology. The benchmark aims to rigorously evaluate LCLMs on real-world tasks, showcasing their potential for disruption in various applications.
What are the theoretical or practical benefits of using the long context frontiers LOFT benchmark in evaluating long context language models, LCLMs?
The long context frontiers LOFT benchmark offers several theoretical and practical benefits in evaluating long context language models, LCLMs. The benchmark allows for automatic creation of increasing context lengths, spanning up to 1 million tokens and potentially scaling further, ensuring rigorous evaluation as LCLMs continue to evolve. LOFT covers a wide range of tasks across text, visual, and audio modalities, pushing LCLMs to their limits and gauging their real-world impact. It focuses on areas where LCLMs can disrupt traditional approaches, such as retrieval, retrieval-augmented generation, SQL-like reasoning, and many-shot in-context learning. By providing a diverse set of tasks and datasets, LOFT enables comprehensive evaluation of LCLMs' performance on complex, long-context tasks useful in real-world applications. Additionally, LOFT promotes the optimization of LCLMs through techniques like corpus in context, CIC prompting, which allows for direct ingestion and processing of entire corpora within the context window, streamlining model development and enhancing reasoning capabilities. Overall, LOFT facilitates a thorough assessment of LCLMs' capabilities across various modalities and tasks, highlighting their strengths and areas for improvement in handling long context scenarios effectively.
How were the state-of-the-art LCLMs evaluated on the Long Context Frontiers LOFT benchmark, and what were the key insights revealed from the evaluation results?
The state-of-the-art LCLMs were evaluated on the Long Context Frontiers LOFT benchmark by benchmarking them against specialized models without any task-specific fine-tuning. Specifically, Google's Gemini 1, 5 Pro, OpenAI's GPT-4o, and Anthropic's Claude 3 Opus were evaluated on tasks spanning text, visual, and audio modalities across various datasets within LOFT. The evaluation involved comparing the performance of these LCLMs with specialized models that had undergone extensive fine-tuning or pipelining for the target task. The key insights revealed from the evaluation results include the following. 1. At the 128K token level, LCLMs like Gemini and GPT-4o rival the performance of specialized models like Gecko in textual retrieval tasks, showcasing the potential of LCLMs in this area. 2. LCLMs, particularly Gemini, outperform specialized models like Clip in visual retrieval tasks across different benchmarks and context lengths, demonstrating their versatility and effectiveness in this domain. 3. Gemini 1, 5 Pro demonstrates comparable performance to a specialized model in audio retrieval tasks across multiple languages, indicating the robustness of LCLMs in handling diverse modalities. 4. In retrieval augmented generation (RAG) tasks, LCLMs like Gemini 1, 5 Pro outperform RAG pipelines on multi-hop datasets, highlighting their ability to reason over multiple passages within the context window using techniques like chain-of-thought reasoning. 5. Closed-book ablations on Gemini 1, 5 Pro reveal that removing the corpus from the context significantly lags behind the long context and specialized models, emphasizing the importance of leveraging external corpora for enhancing reasoning capabilities. 6. LCLMs show reasonable performance in SQL-like compositional reasoning tasks, indicating potential for handling complex structured data without task-specific tuning, although they still lag behind specialized pipelines due to decades of work in semantic parsing and SQL. 7. Many shot in-context learning evaluations show that Gemini 1, 5 Pro outperforms GPT-4o on various benchmarks, with Claude 3 Opus achieving the best performance on average, suggesting the scalability and effectiveness of LCLMs in handling multiple examples within the context. 8. Ablations over different facets of the CIC prompt design demonstrate the effectiveness of task-specific instructions, chain-of-thought reasoning, and shared corpora in enhancing LCLM performance, underscoring the importance of these design choices in optimizing model outputs.
What were the primary results and outcomes achieved by evaluating Google's Gemini 1.5 Pro, OpenAI's GPT-4o, and Anthropic's Claude 3 Opus on the Long Context Frontiers LOFT benchmark?
The primary results and outcomes achieved by evaluating Google's Gemini 1, 5 Pro, OpenAI's GPT-4o, and Anthropic's Claude 3 Opus on the Long Context Frontiers LOFT benchmark revealed that Gemini 1, 5 Pro performed comparably to a specialized model, Gecko, in text retrieval tasks at the 128K context length. Additionally, Gemini 1, 5 Pro outperformed GPT-4o across all visual benchmarks in tasks such as text-to-image and text-to-video retrieval. In audio retrieval tasks, Gemini 1, 5 Pro demonstrated comparable performance to a specialized model, PaLM-2DE, across multiple languages. Furthermore, in retrieval augmented generation RAG tasks, Gemini 1, 5 Pro surpassed a specialized RAG pipeline on multi-hop datasets like Hotpot QA and Musique. However, the performance of LCLMs, including Gemini 1, 5 Pro, declined when scaling the corpus to millions of tokens, indicating room for improvement in handling larger contexts. The results underscored the potential of LCLMs in various tasks such as retrieval, generation, and reasoning, while also highlighting the need for further research to enhance their robustness and performance in long context scenarios.
What are the limitations or drawbacks identified in the Long Context Frontiers LOFT benchmark and the evaluation process of LCLMs, as discussed in the paper?
The limitations or drawbacks identified in the Long Context Frontiers LOFT benchmark and the evaluation process of LCLMs include the following. 1. Existing benchmarks fall short in evaluating LCLMs on truly long context tasks useful in real-world applications, relying on synthetic tasks or fixed-length datasets that do not keep pace with the evolving definition of long context. 2. The need for rigorous evaluation on paradigm-shifting tasks to realize the full potential of LCLMs is highlighted. 3. LCLMs show lag in performance on complex multi-hop compositional reasoning tasks, indicating room for improvement in this area. 4. There is a large performance variance depending on prompting strategies like chain-of-thought reasoning, underscoring the need for further research to enhance LCLM's robustness and instructability. 5. The efficiency of encoding a 1 million token context is mentioned as slow and computationally expensive, despite the compatibility with prefix caching in autoregressive language models. 6. The performance of LCLMs degrades when scaling the corpus to millions of tokens, suggesting challenges in handling larger contexts effectively. 7. The need for more challenging datasets, such as in the audio retrieval task, is indicated to further push the capabilities of LCLMs. 8. LCLMs show lower performance compared to specialized pipelines in tasks like SQL-like reasoning, indicating room for improvement in handling complex structured data without task-specific tuning. 9. The closed-book ablations reveal that LCLM's performance significantly lags behind when the corpus is removed from the context, emphasizing the importance of leveraging external corpus for enhancing reasoning capabilities. 10. The study on CIC prompt ablations highlights the impact of different prompt design choices on performance, indicating the need for careful consideration in designing prompts for optimal LCLM performance.